Mastering algorithm analysis through amortized complexity. Understanding how algorithms perform is crucial in computer science, especially when optimizing code efficiency. The key lies in analyzing time and space complexity accurately. This guide dives deep into amortized analysis, a powerful technique that helps evaluate average case performance of data structures and algorithms over sequences of operations. The fundamentals of algorithm efficiency. Before exploring amortized analysis, we must grasp basic measures of algorithm efficiency. Time complexity quantifies computational steps relative to input size. Space complexity assesses memory usage during execution. Both are critical but sometimes misleading as they represent worst-case scenarios rather than real-world averages. Big O notation provides standardized expressions for these complexities, enabling comparisons between different approaches. Diving into amortized analysis offers an alternative perspective by averaging costs across multiple operations. It's particularly useful for dynamic data structures where occasional expensive actions occur infrequently. Unlike traditional worst-case analysis, which might exaggerate resource requirements, amortized methods provide realistic expectations of long-term performance. Three primary techniques exist for conducting amortized analysis: aggregate analysis, accounting method, and potential method, each with distinct applications and benefits. Aggregate analysis explained. Aggregate analysis calculates total cost over a sequence of operations, then divides by number of operations. This approach simplifies complex patterns into average values. For example, consider a dynamically resizing array. While individual insertions may require copying elements during expansion, overall average insertion cost remains constant. This method works well for cases where operation costs vary predictably within fixed bounds. The accounting method approach. The accounting method assigns credits to each operation based on its actual cost versus what it can afford to pay. These virtual funds help cover future expensive operations. In practice, this means some operations might be charged less than their true cost while others receive extra credit to handle spikes in demand. This technique allows maintaining balance without needing precise predictions about future needs. Unpacking the potential method. The potential method introduces a concept called potential energy stored in the system state. Changes in this value determine effective cost of current operation. If an operation increases the potential, subsequent operations benefit from reduced apparent costs due to previously accumulated resources. This method excels at capturing dependencies between successive operations through cleverly defined potential functions. Real-world applications of amortized techniques. Dynamic arrays exemplify perfect candidates for amortized analysis. Resizing involves significant overhead but occurs rarely compared to regular inserts/deletes. Data structure implementations like hash tables also leverage amortization principles to manage collisions efficiently across many operations. BSTs and heaps demonstrate similar behavior where rare rebalancing events don't significantly impact general performance metrics. These examples show how theoretical models translate practically into optimized software solutions handling massive datasets effectively. Evaluating performance trade-offs. When comparing algorithm choices, always consider trade-offs beyond raw numbers. Memory consumption often correlates inversely with processing speed. Sometimes faster algorithms consume excessive RAM, making them unsuitable for environments with strict limitations on physical storage. Profiling tools help identify bottlenecks by visualizing CPU versus memory utilization patterns under various workloads. Such analyses inform decisions about whether optimization efforts should prioritize reducing runtime or minimizing footprint. Practical implementation considerations. Coding practices influence analytical results unexpectedly. Poor design choices can mask genuine inefficiencies despite good asymptotic bounds. Cache locality matters greatly. The way memory is accessed affects actual runtime even if theory suggests otherwise. Prefetching strategies and memory alignment optimizations become essential in high-performance computing contexts. Awareness of hardware characteristics ensures accurate interpretation of theoretical limits in practical systems. Case study: Dynamic array insertion. Analyze the classic problem of inserting elements into a growing array. When capacity reaches limit, the entire contents get copied to new larger space. Each such resize doubles the available slots. Using aggregate analysis shows average cost per insertion remains constant despite occasional expensive moves. By calculating total operations including copy steps against total elements inserted, we derive the linear growth rate characteristic of this pattern. This case study illustrates why amortized time complexity can outperform naive worst-case estimations in common situations. Advanced topics in amortized cost estimation. Combining multiple techniques enhances accuracy for complex scenarios involving interdependent operations. Hybrid approaches apply different methods depending on phase changes detected dynamically during program execution. Machine learning models now assist in predicting optimal parameters for adaptive algorithms requiring frequent reconfigurations. These innovations pushed boundaries of what was once considered analytically tractable territory. Challenges in accurate amortized modeling. Creating reliable models requires careful selection of representative workloads that mirror expected usage patterns. Overfitting risks arise when using overly specialized test cases that don't generalize well to broader applications. Validating assumptions becomes increasingly difficult as system components evolve independently yet remain interconnected. Ongoing monitoring and recalibration ensure models stay relevant amidst changing technological landscapes. Tools and frameworks for analysis. Various profiling tools support empirical measurement complementing mathematical derivations. Visualizers help trace operation sequences, revealing hidden cost distributions hard to perceive numerically alone. Automated verification systems check formal proofs, ensuring correctness of established bounds before deployment. Integrating static analysis with runtime profiling delivers comprehensive understanding, guiding architectural decisions. Trends shaping future research directions. Quantum computing demands new paradigms for evaluating parallelism inherent in qubit manipulations. Edge devices necessitate lightweight algorithms tolerating sporadic connectivity and limited power supplies. Federated learning environments require secure aggregation protocols protecting user privacy while sharing insights. Emerging fields continue pushing algorithmic research toward novel application domains requiring fresh analytical frameworks. Conclusion: amortized analysis bridges theoretical foundations with practical implementation realities faced daily by developers worldwide. By mastering these principles, programmers gain sharper insights necessary to build scalable, efficient systems capable of meeting evolving industry demands.